Throughout my other RoboDog videos, I've talked a lot about using the hoverboard motors as actuators for the RoboDog, but we can't use hoverboard motors if we don't know how to control them. So, for this video, I'll show you exactly what you need to know to control these heavy-duty motors with the ODrive motor controllers. And by the way, what I'm about to show you won't just be limited to the robot that I'm making. If you want to use hoverboard motors for your own projects that you have in mind, then this video should help you out. If you just want the Python code I wrote to configure the ODrives for the hoverboard motors, I get that. I hate when YouTube videos drag on too long for something that can easily be explained in less than a minute, so the GitHub link for the code is in the description. All you need to do is run the script with Python 3 when you have your motor connected to the ODrive and your ODrive plugged into the computer. After that, your ODrive should be all set to work with your hoverboard motor. But if you think you need a walkthrough on what exactly the ODrive device is, how to install the software tools for it, and how to use it dynamically with the terminal or use it with the Python programming language instead, that's what the rest of this video is for. ODrive is a brushless motor controller, but it's not your average motor controller. It's actually pretty smart. It has a microcontroller that can parse commands to either control the motor or configure the ODrive itself in many ways. The ODrive has a built-in control system that you can configure, and it has various modes that you can set it to, like velocity control mode or position control mode. There are various interfaces for the ODrive device as well, like USB, UART, PWM, CAN, and a few others. The ODrive is capable of many things, more things than I'll be able to cover in this video, so if you want to read up on all the bells and whistles, then you can head on over to the ODrive website to get more information. Link in the description. Connecting the motor to the board is very easy. You can plug the motor phases in any way that you want. I currently have the phases plugged into channel 0. The encoder signals coming out of the hoverboard motor are color-coded. Here's a pinout for what colors go where on the board. Let's now go over some of the software that's involved with ODrive. I'm assuming you already have Python 3 and pip installed, but if you don't, there are several online tutorials that show how to install that. After you have pip, run pip install ODrive in the terminal. This will give you the proper software tools necessary to interface with your ODrive. Once you've done that, you need to run the device firmware update command to make sure that the software running on your ODrive is the latest release. If you get the message at the bottom here, you'll need to swap out a driver on your computer so that you can interface with the ODrive properly. To do this, go to the Zadig website to download their utility, switch the dropdown to libusb-win32, and click Install Driver. After about 30 seconds, everything should be good to go. So now that that's finished, let's dig a little bit deeper into how to use ODrive. First, I'll give you a little tour to show you how things are organized with the Python ODrive tool you just installed. Then I'll show you how to configure and use the ODrive device straight in the terminal. Then we'll repeat roughly the same configuration, but with a Python script. So to start using the Python ODrive tool dynamically, just type ODrive tool in the terminal. This will create an IPython session and load in a bunch of libraries for you to use. If you don't know what that means, don't worry about it. All you need to know is that you're making your terminal aware of all the software packages you just installed. As long as you have your ODrive device connected to your computer with USB, you can type in ODrive 0 to see various attributes of the ODrive's current state. Notice how the VBus voltage is around 27 volts. I can easily request just that number if I use the dot operator like this, and then type in VBus voltage. I can also type in ODrive 0 dot and then hit tab to see all the possible attributes that are in ODrive 0 to choose from. You can also daisy chain these attributes together to go deeper down in the hierarchy. This is pretty much how everything is accessed within ODrive. I plan on just going over the main ones in this video, but I suggest that you check out some of these categories on your own to see what other information that ODrive can give you. So before we configure anything else on the ODrive for the hoverboard motors, let's make sure any previous device configuration is wiped before adding our own. To do this, simply run the ODrive 0 erase configuration command. Our first few configurations are going to be within the axis attribute. Since you can connect up to 2 motors to ODrive at a time, the axis refers to which motor channel you want to work with. Both axes have the same type of attributes, so let's just focus on axis 0. So within axis0.motor.config, there's an attribute called pole pairs. There are 15 pole pairs in the hoverboard motor. You get that number by taking how many magnets there are in the motor, which is 30, then dividing by 2. Next up is the resistance calibration max voltage, the requested current range, and the current control bandwidth, which we will set to 4, 25, and 100 respectively. Because the hoverboard motors are much higher resistance compared to what you would see in hobbyist aircraft motors, we want to use a higher voltage for the resistance calibration max voltage attribute than the default, which was at 2. This in turn means that we want the current sense gain to be more sensitive, so we'll set this to 25 since it originally was at 60. The motors are also high inductance, so we need to reduce the bandwidth of the current controller from the default of 1000, so we'll bring this down to 100. Last up for the motor.config category is the torque constant. The torque constant is a property of the motors and is often included in the motor spec sheet if you're lucky enough to have one for your motor. Unfortunately, these hoverboard motors came with no spec sheet. There are tests you can run with your motor to determine its torque constant, but luckily people within the ODrive community have already figured out what the torque constant should be, which is roughly 8.27. If you want to find out exactly how they derived the torque constant, I'll put a link in the description that goes over their setup and experiment. So now let's configure some attributes for the encoder. For this setup, we are using the encoder that's built into the motor, which are Hall effect sensors, so we want to change the encoder mode to encoder mode Hall. Next, we want to specify the counts per revolution, which is 90. This would normally be specified in the motor spec sheet, but because we don't have one, we had to figure out this number ourselves. I did a video early in the RoboDog series deriving this exact number in case anyone missed it or wanted a refresher on how to figure it out. Because the Hall sensors are low resolution feedback, we need to increase the calibration scan distance from around 50 to 150, so we can get better accuracy for the encoder calculations in the ODrive. Last thing to change in the encoder configuration is the bandwidth. Since the Hall feedback only has 90 counts per revolution, we want to reduce the velocity tracking bandwidth from 1000 to 100 to get smoother velocity estimates. Now that we have the motor and encoder configured, one of the last things to configure is the built-in controller. The built-in controller is a cascaded style position, velocity, and current control loop that looks like this. Let's first start with configuring the position and velocity gains of the controller. Let's set the position gain to 1 and the velocity gain to 2% of the motor torque times the encoder's counts per revolution. This will give us a modest velocity gain of around 15 that shouldn't whipsaw things around too much when the motor's trying to go from the current position to the desired position. We'll also put an integrator gain at 10% of the motor torque times the encoder's counts per revolution, which is an integrator gain of about 74. Also for safety, we will limit the velocity to about 10 rotations per second. Because we want to be able to set position inputs instead of velocity inputs for the motors in RoboDog, we will set the controller's config mode to control mode position control. Now we need to reboot the ODrive board for some of these settings to take effect, but before we do that, we need to save all the configurations we've done so far. We do that by running the odrive0.saveconfiguration command. Now let's reboot with the odrive0.reboot command. Now that ODrive is rebooted with the configurations we just set, we now need to let ODrive run its own configuration. These next few steps will require your motor to be free of any load and be able to move freely. So now let's activate the automated calibration sequence with axis state motor calibration. You should also hear a beep during this step. Once that is finished, make sure that you have no errors within the motor.error attribute. You should also check to make sure that your phase inductance and phase resistance looks reasonable. Here are the values that I got for those attributes. If this all looks good, then we should tell ODrive that saving this calibration to persistent memory is okay the next time we run the save configuration command. Now that we are done with the automatic calibration with the motor, we need to do the automatic calibration for the encoder. Doing this calibration makes it so that it doesn't matter how you originally plug in the motor phases to ODrive. However, after this calibration, you shouldn't change how you plug in the motor phases. To activate this encoder calibration, you put the ODrive in the axis state encoder offset calibration state, again making sure the motor can turn freely. After the encoder calibration is finished, check to make sure there are no errors. If there are no errors, then check to make sure that the offset float attribute is either around 0.5 or around 1.5. Here's what my offset float looks like. If it looks good to you, then just like we did with the motor calibration, tell ODrive that the encoder calibration it just did is okay to save to persistent memory with setting the pre-calibrated attribute and encoder config to true. Now that we were finished with that, the last thing to do is save the configuration and reboot with the following commands. The configuration is now completely finished. Now we can tell ODrive to activate closed loop control by setting the requested state to access closed loop control. Now, if you try to move the motor, it will try to stay in its original position. The longer you try to hold it in offset position, the harder it will try to push the motor back to the desired position. Let's try to move the motor to another position, say 1 full rotation from its current location. All you need to do is set the input position attribute within the controller. If you want to go half of a full rotation at 180 degrees, you can do that too by setting the attribute to 0.5 and so on. I'm able to feed position values into the controller because I originally configured ODrive to be in position mode with the control mode position control value for the control mode attribute. We can easily change that to velocity mode if we wanted by setting the value to control mode velocity control. To set the velocity, we just need to set the input velocity value within the controller. The units are in rotations per second, so if I put 2 here, it'll be 2 rotations per second. If I put 1.5, it'll be 1.5 rotations per second, and so on. To put the motor back at idle where you can move it freely, all you need to do is set the requested state to the axis state idle value. I know this can be very tedious to type in, so I made a Python script to do all this for you that's up on my GitHub. As a side note, I'll be using this repo for all things RoboDog moving forward, so expect this repo to be added to over time as the project grows. So this code does the same exact thing that we just did manually, and then it runs a little test at the end to move the motor at 30-degree increments to make sure it's working right. I'll run this right now to show you what it looks like. Because the encoder that's built into the hoverboard is not very high resolution, it doesn't have the fine-grained control that you would expect when it's moving at 30-degree increments. As I mentioned in some of the previous videos, I plan on using a higher resolution encoder so that I can hopefully have more accurate movement, but it's nice to establish a baseline with the built-in hoverboard motor encoder so I can see the difference between the new ones and the ones I'll be adding. I'll probably also be adjusting these configuration values as I get further along in the project. If I find better configuration values, I'll make sure to update the script on my GitHub. So that's all there is to it. I look at all the comments, so if you have any questions, just ask. Thanks for watching.